Hi everyone! This lecture corresponds to section 18.4 of the openstax astronomy text. The material here should allow you to identify the physical characteristics of stars that are used to create an HR diagram and describe how those characteristics vary among groups of stars, and to discuss the physical properties of most stars found at different locations on the HR diagram, such as radius and, for main sequence stars, mass. In the early 1900s, a Danish astronomer named Hertzsprung and an American astronomer named Russell independently decided to make graphs of stellar properties. These graphs revealed previously unsuspected patterns among the properties of stars and ultimately unlocked the secrets of stellar life cycles. What Hertzsprung and Russell plotted was stellar luminosity versus spectral type or temperature. We call these plots Hertzsprung-Russell diagrams, or HR diagrams. The luminosity on the vertical axis is given in units of the sun's luminosity. The spectral type on the horizontal axis represents stellar surface temperatures. The temperature decreases from left to right. Each position on the HR diagram represents a unique combination of spectral type and luminosity. For example, our sun is spectral type G2 with a luminosity of 1 solar luminosity. On the HR diagram, stars near the upper left are hot and luminous, stars near the upper right are cool and luminous, stars near the lower right are cool and dim, and stars near the lower left are hot and dim. An HR diagram also provides information about stellar radii. Remember, a star's luminosity depends on both the surface temperature and surface area. Specifically, luminosity is proportional to temperature raised to the 4th power times the radius of the star squared. For two stars with the same surface temperature, one can be more luminous than the other only if it is larger in size. For two stars with different temperatures to have the same luminosity, the cooler star must be larger to keep up in luminosity with the hotter star. Stars do not fall randomly throughout the HR diagram, but cluster into 4 major groups. Most stars fall somewhere along the main sequence, the streak that runs from the upper left to the lower right of the HR diagram. Our sun is a main sequence star. All of the stars on the main sequence have something in common. They are all fusing hydrogen into helium in their cores. The mass of the star determines both the surface temperature and the luminosity. The hottest and most luminous main sequence stars have high mass. The coolest and dimmest main sequence stars have a low mass. This orderly arrangement along the main sequence tells us that mass is the most important property of a main sequence star. The fact that mass, surface temperature, and luminosity are all related means that we can make an estimate of a main sequence star's mass just by knowing its spectral type. For example, any hydrogen-fusing main sequence star that has the same spectral type as the sun must have about the same mass and luminosity of the sun. Note that this relationship holds only for main sequence stars, not for giants, supergiants, or white dwarfs. A star is born with a limited supply of core hydrogen and therefore can remain as a hydrogen-fusing main sequence star for only a limited time. This is called the star's main sequence lifetime. Stars spend the vast majority of their lives on the main sequence. Massive stars near the upper left of the main sequence have shorter lives than the low-mass, cooler, and dimmer stars on the bottom right of the main sequence. Even though more massive stars have more hydrogen to start with, they fuse their hydrogen into helium so rapidly that they end up with shorter lives. The smaller stars are simply more fuel efficient. Our sun will spend a total of 10 billion years on the main sequence, fusing hydrogen into helium. For comparison, a 10 solar mass star will only spend 10 million years on the main sequence. A much smaller star, one with 1/10 of that of the mass of the sun, will spend 100 billion years on the main sequence. This is longer than the age of the universe, which we know to be about 13.8 billion years. To sum up main sequence stars, high-mass stars are larger, bluer, brighter, and shorter-lived. The low-mass stars are smaller, redder, dimmer, and longer-lived. The stars in the upper right are called supergiants and giants because they are very large in addition to being very bright. Arcturus, for example, will be much larger than a main sequence star of the same temperature because Arcturus is more luminous. Similarly, Arcturus will be larger than a main sequence star of the same luminosity because Arcturus is much cooler. Remember, it has to be larger to keep up. Giant and supergiant stars are nearing the end of their lives. They have already exhausted their supply of hydrogen in their central cores. At this point, the stars puff out their outer atmospheres and become larger and redder. This figure shows one of the largest supergiant stars in our galaxy, VY Canis Majoris, compared to the Sun and the Earth's orbit. Not all supergiants are as large as VY Canis Majoris, but they are enormous when compared to stars like our Sun. For example, Aldebaran in the constellation of Taurus and Arcturus in the constellation of Boötes are both more than 10 times as large as our Sun. And Betelgeuse is a supergiant with a radius of about 1,000 times that of the Sun. Stars near the lower left of the HR diagram are small in size and pure white in color because of their high temperatures. These stars are called white dwarfs. White dwarfs are actually dead stars. When stars like our Sun run out of nuclear fuel, they become white dwarfs. They are as massive as the Sun, but only the size of Earth. We've already learned about the spectral classification scheme for temperature. Astronomers also assign each star a luminosity class, which describes what region of the HR diagram the star is in. The classes are designated with Roman numerals 1 to 5. Luminosity classes 1 to 4 are giant stars, and luminosity class 5 are main sequence stars. For example, to describe our Sun, we say it's a G2 luminosity class 5 star. This tells us the temperature and the fact that the Sun is on the main sequence. The star Sirius is also on the main sequence, but with an A1 spectral type, it is much hotter. And Betelgeuse is an M2 luminosity class 1 star, which tells us it is a cool supergiant. That's all for now. Take care, and I'll talk to you again soon.